Hello there, my aspiring calculus student or students, however many people are watching this. I always want to introduce these videos by saying, hey everybody, what's going on? But realistically, how many people are watching these YouTube videos at one time? Probably just one person is sitting there going, yeah, everybody, it's just me. Anyway, today in this video, what I'm prepared to show you is we're going to get into some properties of definite integrals, where we're going to start introducing the idea of integration into or with calculus, meaning that what we have done so far up to this point in calculus is we've established how we find the area of a triangle or the area underneath a curve by utilizing some basic geometry shapes like rectangles or trapezoids and left or right hand or midpoint Riemann sums. And just like with derivatives, we can go to an infinite number of rectangles underneath a curve and approach what the area is going to be. And that is where we're starting to go here. Now, we're not going to get all of the types of different or integration that we can do here yet. Most of what we're going to be looking at here is just kind of introducing you to the idea of, you know, what are the properties of integrals? How do you read an integration notation? And they're going to kind of keep it simple with geometry shapes, okay? Rather than jumping ahead into what the fundamental theorem of calculus is going to tell us and show us how we do integration that way, although that's coming. So here in this section, we are moving beyond the finite sums, and we're going to be exploring what happens in the limit. Now, that's not entirely true. Again, we're still kind of sticking to geometric shapes as opposed to just rectangles. So we're going to have some circles and trapezoids and rectangles and things to look at too. But for the time being, we're going to utilize mostly positive values. However, it's telling you we are now going to be looking at some negative values, meaning that the area underneath the curve or the area contained by the curve in the x-axis will now actually be below the x-axis, meaning that an area that's contained below the x-axis by a function is going to represent a negative area. Okay, so that is going to be applicable for if you're having to do a net area over an interval that both has something above the x-axis and below the x-axis at the same time for that. And that's essentially what this little bit here is telling you, is that you will, just like any other net thing, like with money, you have money come in, you have money go out, and then you have a net, and that is what think about your taxes on your paycheck. You earn so much money, the government takes something out, and the net is yours, not the gross. And that's kind of what this little diagram here is. And those of you that are watching the video, following along with the notes for this lesson, this isn't in the handout for the notes, but it's just a visual aid to illustrate what we're talking about when we have something contained by the x-axis in the curve, both above and below the x-axis. The yellow region would be positive, the green region would be negative. So that's all that's kind of illustrating. Now here we're looking at the definite integral, and there are two types of integrals that we see generally in calculus. There is a definite and an indefinite integral. And the difference between them is that a definite integral is going to have these things here. It's going to have a lower and an upper bound associated with it. And again, just like with differentiation, we had to do derivatives with respect to x. We're still doing integration with respect to x also. So this next bit here is going to show you the parts and understand what we're looking at. So the integral sign itself is called the long S symbol, or just the integral sign if that's what you want to think of it as. Meaning, and I had this in my Riemann sum video too, this is called the long S. It's like you take the letter S and you stretch it vertically. I think I may have seen it in some instances spelled like that, long S, but anyway. Uh, the lower part, the A value, that is the first value on the interval that you're finding the area under the curve for, the lower bound. The upper bound is the second value of the interval that you're finding the area under the curve for. The upper bound is B. The actual function itself, whatever that happens to be, linear, quadratic, exponential, doesn't make a difference. That is referred to as the integrand. X is showing you that that's the variable that we're taking the integration with respect to. And so here we're taking the integral of function f along the interval from a to b. Okay? So that is how we read the notation for definite integration. And here it's kind of giving you just the mathy definition, but it's going to be continuous, non-negative. That's again, I don't think of that in terms of that you can't have negative values with integration, because you absolutely can on a closed interval, bounded by some region. So there's not going to be a vocabulary quiz here, so you don't need to actually associate the definition with the term. You just need to be able to know how do you actually do integration and what are the properties that we do integration with, and that's what we're going to be focusing on now. So here we're seeing our first example of how we're going to be doing integration of areas under the curve. And you can see we have regions bounded by something above the x-axis and something below the x-axis in this case, contained in the closed interval from -8 to +13. And they're specifically keeping them simple geometric shapes. So if you look here, let's see this guy, that's the triangle. We have a semicircle, then we have two trapezoids on the right side of the y-axis. So we're not getting into proper like polynomials or proper curvy functions that we would find the area underneath the curve for yet. That will be more when we start talking about what the fundamental theorem of calculus is and how you do definite integration at that point. It's not that hard, but this is just introducing you to the properties and to the idea of definite integration, so we're going to hold off on fundamental theorem of calculus for a little bit. Okay. Now, again, in your notes, if you have the handout handy, you can just kind of refer back to the diagram as necessary, but if you don't and you're just kind of watching this video because you need help with definite integration, I just kind of copied the image over, okay? So for problem number 1, and I guess we'll just do problems 1 through 7 first, so that way we can just kind of keep looking at the diagram where it is. We're looking at the integration, and the function itself doesn't have any specific equation for it because it's made up of a whole, it would just be one really complicated piecewise function. But we're looking at it from 0 to 7. Well, 0 to 7 would be the area of the trapezoid that is above the x-axis. Now, this is where, of course, because these are geometric shapes, you do want to make sure that you remember the formula for the area of a trapezoid. And in this case, the area contained on function f from 0 to 7 would have an area of 20 square units. Now, on problem number 3, notice that the lower bound is actually negative. So we're going further left on the x-axis, and we're going from -6 to 0, which is fine because it's still going to represent a left to right general motion for the interval, as the interval is still increasing from there. So from -6 to 0, that represents the area of the semicircle. So I'm going to find the area of a circle and divide it by 2 or multiply it by 1/2, however you want to think of it as. So here, and again, because it is it's negative because it is below the x-axis. So -4.5 pi units squared. Now, in this case, and I'm going to say that we didn't miss anything. No, we didn't. Okay, because this one here, what it's doing on example 5, because again, I'm just kind of going down through the odd numbered problems here. Example number 5, if you notice, the lower bound is 7 and the upper bound is 0. So we're kind of counting backwards here. And what that is it's kind of a, I guess, if I was an English teacher, this would be an element of foreshadowing. This is going to be one of our properties of definite integration. It is absolutely possible for the interval to be backwards like this. However, when the interval is backwards like this, generally what we're going to do is we're going to take the same area from 0 to 7, which we've already got in problem number 1. Okay, so from 0 to 7 and from 0 to 7, it's the same area of the trapezoid. But because the lower bound and the upper bound are reversed, they're in the opposite order, the sign of the area will change. So it goes from being a positive 20 to a negative 20. And then 7 on this one, from negative 8 to the whole thing all the way up to positive 13. It's just what's the area basically of the whole thing? What's the net area? The positive areas taken away from the subtracted with the negative areas. And in this case here, and it would be helpful, I know I'm skipping by looking at the odd number problems because some of these numbers are going to be taken from other things, but we're finding the area of the triangle at the far left, the area of the semicircle, the area of the trapezoid just to the right of the y-axis, and the area of the trapezoid underneath the x-axis, and we're going to just combine everything. Now we're going to keep it in terms of pi the way that I did it. At least I kept it in terms of pi because, you know, I'm lazy and didn't want to do it as a decimal. So now let's switch on over here. And what I want you guys to do here is, if you feel comfortable enough, go ahead and try doing, and I think this is, I know that there's more problems after this, but this is all I was able to fit on this screen. Go ahead and try pausing the video and see if you can answer the even numbered questions based on what I did as examples 1 through 5 earlier, or 1 through 7, the odd numbers, and just see what you get. So here, hopefully you've paused the video and you've tried working them out, but we'll see what we have. From problem number 2, we're looking at the area from 0 to 13. So that's the trapezoid that's above and below the x-axis. So we're going to take the one that's above and subtract it from the one that's below. So I'm just taking the 20 that we had from problem number 1 and then subtracting the other area. Now number 4 in this case, depending on, you know, hopefully this one didn't really throw you off, because if you notice the upper and lower bounds are the same. It's both at 3. Well, if the upper and lower bounds are the same, it means there's no horizontal motion. So if there's no horizontal motion, it's not possible for us to have a two-dimensional figure, so there's no area. So the integration here on that would just be 0. Problem number 6 is doing the same thing that problem number 5 did. It's reversing the general order of the integration, where the lower bound is actually larger than the upper bound is. So same idea, we're going to find whatever that area is between the 4 and the 10, and then we're going to simply change its sign and make it, you know, from whatever it is, to be positive to negative. Okay. And the last one, the derivative of the function at x is equal to -6, here in this case, because it's at a corner, the derivative at that point is undefined. So here are the last 4, and we'll go ahead and start taking a look at these. Let's see, we'll see if we can kind of fit everything here so we can do them in numerical order this time. So the second derivative of f of +6. Okay, well this one doesn't really need much in the way of integration. You know, the derivative of +6, the derivative of a line, is the slope of the line itself, and so the slope of the line is constant. Its second derivative is going to be 0. And there we go. The average rate of change from 0 to 5 on the function. So from 0 to 5, again, the average rate of change, just do your difference quotient. And in this case, I'm getting a 4/5. And again, example number 11 here is kind of alluding to one of the properties for integration that we're going to be seeing. So if you notice, it has the sum of two separate integrations from 0 to 2 and then from 2 to 4. Well, because the 2 is the upper bound of one and the lower bound of the other, it's essentially continuous from 0 to 4. So yes, the statement that we have on the left side of the equal sign and the statement that we have on the right side of the equal sign are going to be the same. And over which values of x is not differentiable, basically anywhere there's a corner or a cusp or something like that, which there are several in this case. So at all of those x values, the function is not going to be differentiable because it is because of the corners. The limits of the left and right side aren't going to match. Okay. So that is essentially what we're looking at for definite integration. Now, we're going to start moving away from that piecewise function that's made up of a bunch of geometric shapes, and we're going to be moving on to, I don't want to say complicated functions, but we're actually going to look at functions that we could do a whole bunch of other things that, differentiate it, transform it, graph it easy, things like that. Generally what we think of as a function in math. But first things first, let's take a look at the properties. Here on 1, this is one of the properties that we looked at where the upper and lower bounds were both 3. If I don't have any horizontal motion, then there is no integration, so the area is 0. 2, this is another one that we were seeing on, I believe they were problems 5 and 6. If the function is able to be integrated and the upper and lower bounds are in the reverse order, then essentially we just take, we put them back in their proper places where the lower bound is at the bottom and the upper bound is at the top, but we multiply it by a constant of -1. So we change the sign of whatever the integration happens to be. Here, the additive property, this is essentially what we were just looking at, I believe, on problem number 12, maybe? No, problem number 11, where the upper and lower bounds were the same. This is very similar to the transitive property in geometry. If this and this are the same, then we can go directly from here to here, and that's kind of what we're seeing with that. And again, here moving on to the next one, we haven't seen these yet. If you have a constant, which they're labeling here as k is a constant, if you have a constant multiplied to your function for your integrand, you can actually factor that out and kind of put it to the left side of the long S symbol and then do your integration, and whatever the integration is, multiply it by k. Now, if you're trying to integrate a constant function, okay, a constant function, if you go back to what we understand about functions, x and y axis, a constant function is just a horizontal line. So the integration from there, this is A, this is B, every shape that we have is always going to be a rectangle. So it is the base, or this would be the base, and this would be the height. So that's why we're just saying whatever the k value is, the height of the rectangle multiplied by the base, which would be the difference of the upper and lower bound. And on 6, this is where we're looking at trying to do integration of two separate functions. So you may see functions written or integration problems written as it is on the left, and you would just kind of break it apart and do the integration of function f, then do the integration of function g, and then either add them or subtract them, whatever the signs of those happen to be. And here we're doing a little bit of abstract kind of integration using those properties. We're not actually using a figure so to speak. So for instance, the example that you have in A, if you notice, the upper and lower bounds are switched based off of what they're showing you in the given information, where the integration from A to B is supposed to be equal to 8. So if we're switching the integration order, I'm sorry, if we're switching the order of the interval to be the upper bound to the lower bound, we just change the sign of whatever it was multiplied by a -1. Here, this is where we have the constant multiplied to whatever the function happens to be. So this is the property where you can kind of pull that 2, the constant, out of the integration itself, and then do whatever the integration is. So here we're saying the integration from a to b of function f, which was given to you to be 8. So you take that 8 and multiply it by the constant of 2. So the final integration would be 16. And here, there's just a few more. Go ahead, and up at the very top, so again, if you're following along with the notes for this course, then you don't need to refer back to it. But if you're just kind of watching this video because you just found it and you needed some help with definite integration, I just kind of copied the given information from the last slide to here so everybody can still see it on the whatever device they're watching on. Now here on C, this is the integration of a constant from a to b. So the constant itself is 5. So we're going to say 5 multiplied by the base. Now we don't know what the actual value of the base is. We just know it's going to be the difference of b minus a, whatever that happens to be. And example D, this is kind of where we're taking two separate functions. We have the integration of the constant of 5 plus the integration of function g from a to b. So we can kind of separate it like that. And we've already actually answered the integration on the left where we have the constant of 5. And all we have to do is figure out what the function for g would be, which is given to you to be a -3. So if we say plus a -3, we just say minus a 3. And we can't, you can distribute if you wanted to, but there's no reason to, so I'm just stopping there for my answer. And E is basically the same thing as D, where we have the sum or in this case, the difference of two functions. So I'm going to say the integration of function f minus the integration of function h, both along the interval from a to b. So here we have 8, which was given to me, minus the 5/2, which again was given to me, and we just take the difference of those, and we have 11/2. And finally, here, this is that last one. We haven't, or not the last one, but we haven't seen this one just yet. This is the one where they're kind of taking the upper and the lower bound and kind of marrying them together, so that way we can just say, well, we're looking at it from A to B, okay? And that is what was given to you. Let me bring that down a little bit so we can see. So this is that third property. So we're able to show that we're just looking at the integration of function h from a to b. So we can just take the value of 5/2 that was given to me and say, okay, that's it. We're done. So that's how we're looking at the properties. Now this last one, or this next example here, it's still kind of picking up on the things that we were doing with the properties. But what it's telling you to do, it says find the following. If we had this integration from 1 to 5 for the function 3 times whatever function f is plus 4, it's asking us to actually find what is the integration, or what is the integral that we're supposed to use. So we kind of treat that just like if it was x itself. Okay, so this is not really a calculus problem. This is really just a simple algebra problem. We're trying to get the integral by itself. So, we take the properties of the integrals and we can separate them because we have the constant of 4. So it's like saying 3x plus 4 is equal to 34. Now we are going to use the properties here a little bit. We're going to say the integral of the constant, we can say that's going to be 4 minus or 4 times the difference of the interval, with, so we say 4 minus 5 times 1, and that's, going to just give you a 16. And now we move the 16 over through subtraction, there we go. And then we divide it by 3, and here we go. That's like I said, it's mostly just a very simple algebra problem. It looks complicated because it has that integral symbol in there, and brackets and parentheses, and just, oh, it looks so intimidating, I guess. But we had just two very simple calculus concepts of not even real integration. I guess we had one, but not the most impressive question. But it is, it is what it is. That's what we would do to answer that question. So I'm sure I shouldn't complain or shouldn't criticize, because it's not like I would probably have something fantastic if I tried to write my own curriculum for every single problem. But anyway, here, this is where we're kind of marrying things that we can do with integration with properties on functions in general that you probably would have seen from pre-cal, with the idea of an even function or an odd function. Now, specifically, if you think about an even function, it's going to be symmetric to the y-axis. So here, this is kind of an example. Now, I don't know if the function is supposed to be quadratic. I'm just giving an example of what an even function is, being symmetric to the y-axis. So they're showing us that on the interval from 0 to 3, the area underneath the curve there at that point is going to be 8, which I've kind of highlighted. So it's asking, what is the value of the integration from -3 to +3? Well, we don't know anything about -3 to 0 or anything, but maybe we do. Because it's symmetric, the area underneath the curve from 0 to 3 on the right side and the area under the curve from 0 to -3 on the left side must be the same, because the functions are congruent on both the left and right side of the y-axis. So in this case, we can just conclude, because it's symmetric to the y-axis, that the area on the right and the left side should be the same, because the distance is the same on both sides, and that's how we're going to say that the total area is just 16. Now here, for an odd function, okay, oh, hit the wrong button first. Let's go back. Pretend you didn't see that. There's my graph. Okay. So an odd function is symmetric to the origin, or symmetric to the y is equal to x line. So here is just y is equal to x. So it's obviously symmetric to the origin. And it's kind of doing the same thing from 0 to 3. It's telling you that the area underneath the curve at that point is 8. So what can we conclude about the area from -3 to +3? Well, similar to what we did with the even function, the area bounded by the curve and the x-axis in both cases, because the distance that we travel horizontally left or right is the same, and the area of both parts will be the same. However, because the area on the left that you're seeing in the graph is below the x-axis, it would be a negative area. So the net area cancels. It becomes 0. And that's what we would look at here. Now these next bits here, most of these examples, I'm going to kind of show you a couple of ways to do it. I'm going to show you just based off of what the function would be, how we could find the area, or how we could use it with the properties that we were seeing earlier in the lesson. So do it whichever way you prefer. The way that I'm going to show you, where we actually graph the function and find the area underneath it on the interval using some geometric formula, or break it apart and look at it in terms of the properties of integration. And let me illustrate with the first example here, and you'll see exactly what I'm talking about. Here, where the integrand they're giving us is it's no longer a generic kind of f of x, g of x function. It's an actual linear expression. And they're showing us that we want to integrate it from from 1 to 4, which is no big deal, right? We can all graph a line, so that's what I'm doing. I just graph the line, and I shade in the area underneath the line from 1 to 5, or from 1 to 4, and now I have a trapezoid. And I'm going to find the area of the trapezoid and see what I get. Now here we can do the same thing with our properties of integration. Sorry, I stepped out of the matrix there for a second and had to reboot myself or something. So what we're going to do is we're going to look at the parent function of whatever happens to be. In this case, the parent function is just y is equal to x. Now we're still looking at it on the same interval, okay? But based on what we're doing is we're going to break it apart into two separate integrals based on the properties. We can take the derivative of x by itself, which is why we're using the parent function, plus the integration of the constant of 3. Does that make sense? So the derivative, I'm sorry, not the derivative, the integration of the function for x itself is still that trapezoid region here. We're still finding the area of this trapezoid here, okay? But we're also adding the area of the constant. So in this way, it's kind of like we're doing, more work than is necessary. But that's just my opinion. Some people may not see it that way. But we have the integration of the stuff underneath the constant and the stuff of, said that backwards, the integration of the area underneath the line itself, y is equal to x, and the area of the constant added together, it still gives us the same result. So that's what I mean by saying that we could just graph the function and find the area underneath it, depending on the shape that you have, or you could actually use the properties of the integration. And I'm going to do the same thing here. I want you to go ahead and pause the video and try working this out using one method or the other. It doesn't make a difference to me. Just see if you can get the area underneath the curve here. And when you're done, push play and, hopefully celebrate. In this case, I have another linear function, which I'm going to just graph based on what they gave us. And that would be the graph right there. And the area underneath the curve is, again, a trapezoid. It almost looks like a triangle because, that one base is only 1 unit long. But we can just count how long the two vertical bases of the trapezoid are. And we can count the length of the horizontal base of the trapezoid. And, again, go to the trapezoid rule here, and there's our area. Or we can use the properties of integration where we look at it with breaking it apart, so the function that we would have would just be y is equal to x, and in this case we're going to say the derivative integral of the constant 4 minus the integral of the function x along the interval from -1 to 3, and work it out the same way. So in this case, the constant would just be 4 minus, or 4 times the difference of the bases, which would be a 4 again. And then we're going to subtract the area of the stuff x here. And now if you notice in this case, we actually have two triangles that we had to find the area of. I have to find the area of this little triangle here, and I had to find the area of this bigger triangle here. So again, in this case, it seems like I'm giving myself a little bit more work to do to get to the same answer. But maybe graphing the parent function is going to be easier and you prefer doing that as opposed to what I did originally on the left, where I graphed the actual function. Now for this one here, this one's going to get a little, a little bit tricky, because maybe we remember what that function looks like, maybe we don't. The square root of 4 minus x squared, that is going to be the area, or the function for a semicircle based around the origin with a radius of 2 in this case. So there's no motion horizontally or anything like that. It's just we have the radius of 4, going back to your formula for area of a circle. Area of a circle x squared plus y squared equals r squared. Okay, so the radius here, of course, there's the x squared term part, but anyway, that's the shape of that particular function. And this one I really can only do one way. I can't, I don't want to try to take the function that we have there and try and break it apart. So I'm going to just look at the integration of the semicircle and find the area that way. And there we go. And the next one is pretty similar. The only difference is, now in this case, I can do it two ways. I can do it, by graphing the actual function. So if you, paid attention to what we did on C, you could recognize that we're definitely utilizing a semicircle again, something that's going to be centered around the origin with a radius of 3, but it's also shifted up vertically one space. And so this would be the actual graph. Now the interval that we're looking for is from -3 to 0. So I'm not looking for a semicircle area here. I'm looking for a quarter circle area plus whatever the little, vertical shift that bumped it up was. So we have those two shaded areas of that purple and turquoise, I guess. So we have a quarter circle and we have a rectangle, and we're looking for the area of those. So there we go. 9 pi over 4 plus 3. Now in this case, we don't need to graph the actual function. We can graph look at it in terms of, the actual properties of the integration. I can break it up into two parts. The integration of the constant 1 plus the integration of the semicircle itself. And I will wind up with the same thing, looking at it from -3 to 0. And this is how we would end up, come on, where is it? There we go. How we would end up at the same point, whether we just graphed the function, graphed the actual integrand itself, and then found the area underneath for the interval given to us, or by looking at the properties of the integral and breaking them apart into two separate ones. Now here, this function g, this is where, I don't know, I don't want to say things are going to get really any tricky, but it's same idea. It's a linear function for our integrand, and if I were going to just graph, if I wanted to know the area of the function, I'm going to just kind of graph the function, and I have that trapezoid where I'm going to find the area. There we go, 28.5. Or we can again use the properties of the derivative or of the integral itself, and we can break it up using two properties. So we can take the 3x as one integration where the 3 is pulled out as a constant, and then we take the integral of just the y is equal to x function from 1 to 4, and the integration of the constant 2 also on the interval from 1 to 4. Either way, you're going to get the same answer. Now this last one here, this is the only one that I could have done it two ways, and I just really didn't have it in me to type all that stuff up. So I didn't. And I want to say, I think this is where we're starting. Yeah, okay. So graphically, these are the two functions that we would have, and the one on the semicircle on the left really, if we were doing the function itself, we would have bumped it up one space to the, one space up. But anyway, I'm going to just use the properties of the functions themselves rather than try and, I didn't want to do this one two ways. Like I said, I just didn't have it in me. So we're going to break up the interval from 0 to 2 to two separate integrations themselves, one for the constant of 1 and one for the radical expression 4 minus x squared. And we'll do the same thing with the second integration from 2 to 5 and go from there. And here I could have kind of combined them from 0 to 5, but I didn't think it was worth the effort of trying to put the functions as one type of function, so I'm just keeping them separate. That's why I'm, this one I just felt it was just easier to use the properties of integration and keep everything separate. So here, this is what we're getting for our integration for the constant of 1 from 0 to 2, and the the quarter circle that we're looking at again from 0 to 2. And I think I shaded the wrong side. I should have shaded the right side of that from 0 to 2, but I shaded the left side of the semicircle, so my apologies on that. And then you just kind of keep going, the derivative of the constant 3 from 5 to 2, and just plug in your numbers and see what you wind up getting, and here is your final value for your integration, 1/2 plus pi. And that, ladies and gentlemen, is going to kind of conclude the examples that we have for the properties of definite integration. Keep in mind how we read it as far as upper and lower bounds, where they're located, that the functions themselves, they can really be any kind of functions, but in this case here, we're really just kind of limiting it to things that can give us a geometric shape that are easy to do, because we haven't gotten to the fundamental theorem of calculus yet for definite integration. And the properties, as far as how you can separate an integral to make it a little bit more manageable by breaking it up into pieces if you need to, like we are doing here on example H. But thanks for watching, guys. If you have any questions, be sure to get in touch with me and let me know. I'll be happy to answer any questions that you have. And until next time, guys, be safe, be good, and take care.